Okay, so again, this can I get a level check? Sure. Would you like a level check? Is that okay? I'm not going to turn that up a little bit too long. How's that? How's that for sound? Are you good right now? I think we've got a number of things on the agenda this evening, so I think we'll get started promptly. Welcome, everybody. This is the Victoria Centre of the Royal Astronomical Society of Canada. I'm Chris Pearce, the Centre President. I'd like to welcome everybody here tonight. On our agenda this evening, we have our standard agenda. I think we'll skip the observing reports for tonight because there's a number of other things to cover. We have some announcements. We'll be talking a little bit about the upcoming events. We'll then have our guest speaker, and then afterwards we'll have coffee, tea, and cookies for those who are available in the 4th floor lounge at the Elliott Building. Maybe I'll just cover the events first, and then we'll get into the announcements. So just a reminder that the Victoria Centre Observatories have switched to Friday nights now, although, as we'll hear from the Tech Committee, we're in the middle of switching the telescopes, so we don't have the normal telescope available. Astro Cafe is on Monday evenings. We're still in our temporary location, and I don't think we have a date for moving back into our regular location. No. We're going to try to go with the UVic Observatory this week. So that's open to all members. The meeting place will be out in the lobby here before 7. And weather permitting, we'll send a go, no-go message on Friday afternoon. Okay, and that will be a session on the one of the larger telescopes in Victoria, not the largest. And the other thing I want to mention is we have our annual general meeting and dinner in about a little over 5 weeks, I guess. That will be at Cedar Hill Golf Course, and I'll be taking meal orders and payments if you want to make them tonight. Otherwise, I'll be at Astro Cafe in the intervening time, or you can order by email and pay at the door. Lori is taking calendar orders. Well, I'll mention that while we're here.
Anybody else? Calendars will be $15 a piece. These are from the Royal Astronomical Society in Toronto, and I'm going to put the order in about 1, maybe 2 more weeks. Let another Astro Cafe go by, but they need to be in fairly soon. So just let me know if come and you want. I'm not taking money yet, but I know where you live. So.
Or you'll find out.
Yeah. Okay.
So a few announcements then. I think I've said all the things I wanted to mention. We have 260 members at the moment. So it's been, which is good. Reg, did you have anything?
Well, the Sky News for October focused on the eclipse, and I want to thank all of the people who contributed to this article, this issue. We have a collection of memories and about people's experiences from various areas down in the States and in Victoria. And hopefully this will, if you look at this as years from now, it will help you to recharge your memories and bring it all back again. So thanks again for all who contributed.
Reg, thank you for putting out such an incredible issue.
Les, are you available now? See if I can get this to work. Did you ask me to come on down? I did. You're the next contestant.
What do I win?
Yeah.
There's a few astronomical happenings that are occurring in the next little while. one of them that's been ongoing is the Royal BC Museum's IMAX Theatre is showing The Search for Life in Space. And it's a pretty good movie. A little low maybe on the technical side, but it has fantastic graphics. So what we'd like to do is to organize some kind of opportunity for members to go together, perhaps at a discount, probably at a discount. And just as a quick show of hands, who would be interested in going to see this film in the next month or so? A fair number of people, okay. So I think what I'll be doing is putting a notice out on one of the listservs, and maybe you can get a hold of me, or if you don't see that listserv, just get a hold of Barb or I. That's my wife Barb there. And we'll figure out how to do this. We don't have a date, but maybe there'll be more than one date that turns out to be worthwhile. We did see the original presentation where Lisa Goldenegger, who's pictured here, made an appearance at the IMAX Theatre and answered many questions, and that was fairly engaging. And she's the director of the Carl Sagan Institute and an associate professor at Columbia University. So she's kind of the inheritor of the Carl Sagan, whatever it is that Carl Sagan had. Yeah. Anyway, she's very good too. Next slide, please. Another event which celebrates another aspect of largely American astronomy, but still very interesting astronomy, is the presentation, the theater presentation, Silent Sky, which is being held at the Chemainus Theatre. Probably most of you know that the Chemainus Theatre is located in what city? Anyway, it's a great place to go at times, and Barb and I go there quite often. So we're actually going to see this play on Thursday, October 19th, and would welcome additional people to go. We can probably arrange a 15% discount for those that book through me. But the presentation goes on from October 13th to November 4th, so please go at any time. And it's actually about Henrietta Leavitt, Henrietta Swan Leavitt, who was known as or who has employed as a computer at the Harvard College Observatory late in the 19th century and in the early 20th century. But she was renowned because she actually was the person who discovered the period luminosity relationship for Cepheid variables, which is what has allowed the first large-scale distance measurements of the universe to neighboring galaxies, for example. And she didn't get much recognition during her life, but she still had an interesting life. So that's what Silent Sky is about, and we're looking forward to seeing it. Next slide, please. The last thing I wanted to talk about was, gee, we've got these things about American astronomy largely going on around here, but we want to have a celebration of Canadian astronomy and astrophysics. And a big year is coming up for us next year, 150th anniversary of the RASC, the 100th anniversary of first light at the Dominion Astrophysical Observatory. And there are other big things happening in Canadian astronomy that are leading into the next century of astronomy. So given the prominence that Victoria has in the Canadian astronomical world, and given those anniversaries, the Canadian Astronomical Society happens to be meeting next year in Victoria, and they're going to meet the week of the Victoria Day parade. So what some luminaries came up with, an idea they came up with, is let's have a float in the parade, and this would be part of the commemoration of the 100th anniversary of the Plaskett and a celebration of the next century of Canadian astronomy in some sense. Now, that all sounds nice, but it means we need volunteers to actually come up with the specific ideas about what that kind of commemoration might be. And there's a meeting on tentatively scheduled for October 25th between the leaders of this project, which are from the Dominion Astrophysical Observatory and from the Friends of the Dominion Astrophysical Observatory. But we want to have RASC involved in this. After all, the Plaskett telescope is right in our logo, we should have some involvement in this and be supportive of this broad activity celebrating astronomy, particularly in Victoria. So what we're looking for, someone maybe a little different than the usual suspects, because you want somebody who, or a couple of people, who can sort of vision a little bit and dream up practical ideas that could be implemented in the kind of context of the Victoria Day Parade, and having a float or something that would do this commemoration and make an impression on the community that astronomy is a big time thing in Victoria. And so if there were a couple of people that would volunteer, not necessarily here right now tonight, but if you think about it and you want to find out more information, there's information in the Sky News newsletter that Reg just put out. And you can talk to various people, including Ken or Jim or myself, and we'll kind of tell you a little bit about what might be involved. But what's really involved is your interest and enthusiasm. So this is an opportunity. There will be more opportunities for additional volunteers as we come to the point where we're moving beyond design or the concept, and we're actually building the whatever it is, or putting together the team of people to go marching in the parade, or whatever it turns out to be. So this is not the end of it, but we need somebody to take it by the horns and help make it go. So please see one of those three people, or email us, or read the article in Sky News, or don't just let it drop if you really might have an interest. So thank you. Any questions on any of those things? No questions. Perfect.
Okay, thank you, Les. Bruce.
So as you know, we've, after years of playing Scrooge, unloosened the first swing bit level of Santa this year. Went with the new TV down at the Astro Cafe that we're pretty walled off. And of course, new telescope being installed by our glorious tech committee, putting in long hours on this. So got a lot of new shiny things, which is nice. And just like the last time we got a big telescope project, which was a little before my time as far as membership goes, they passed the hat around and did a really good job. So at this very moment, well, until the next skills come in, we don't actually look like we can spend all this money. So that's really good. Joe Carr did an excellent job fundraising. His ability to shoes is pretty underrated, I think. So I think he did deserve a good hand for that. Did a great job. Our gaming account currently stands at $20. So we did not do any raffle this year due to the whole trying to get the prize hammered down. It just took too late. The timing was a bit off, but it didn't seem like we needed it anyway. Our member account stands at $10,330, and which gives us a lot of freedom if we need to pay for a venue for a star party. We need for some more accessories for BCO that should be in their project. And maybe a few other little things, possibly a public outreach solar telescope of not overly large size would be very nice as well. So we've got funds for a few more things this coming year if we want to spend a little bit more. As long as we don't spend it all, we're pretty good. And that's where we're at. And of course, we just had year end, so we're into a new fiscal year. So once the Canadian Revenue Agency decides to send me forms to do my paperwork, I'll probably get on that. And that's it.
Thanks, Bruce. Any questions for Bruce? Okay, Ken, anything to update?
We only had one outreach event at the Somerset House on Dallas Road this last month. I'd like to thank Diane, Nelson, David for coming out. Appreciate you doing that. Nothing planned for the next month. That's it. Thanks.
Thanks, Ken. Sid? Schools program in full swing?
Yeah, it has taken a little slow to start the program, but it's coming. We have visitation next week. We got night sky viewing coming the week after. And then in December, we are taking part with the STEM program at Glen Lyon Norfolk School. So, yeah, it's coming along. Yeah, it's so.
Great, thank you. Anything on the national front, Nelson?
I have to say that I didn't find anything going on the national front, although I did in reviewing my materials, I see that there's supposed to be a meeting at the end of October, this national meeting, which I and you probably will attend via teleconferencing, but I don't even see it in the schedule. Hopefully we'll have something to report after that.
Great, thank you. Okay, and I think maybe what we've all been waiting to hear, Matt. Technical committee.
Technical committee was just trying to get you a photo here. Show off our shiny, so let's hear yours. Okay.
So I should have it? Or you're just gonna be unplugged?
Yeah.
There it is. So that means it's installed. Or
It is installed. It's there. We bought some new wires to host some new accessories. Rise on an electronic focuser. Down the road, something you might use USB 3 like a new camera. For the meantime, the next concern is getting a new T-point model going with the existing QSI camera that we have. The work that we've done so far is it's on there, it's balanced, and basically it's ready to drive around, but we just haven't tried it out yet. So looking forward to getting first light. Any questions?
What's the date for the first flight? Do you have any?
Well, this Saturday I'm hosting,
Oh,
if
this
it's
Saturday?
clear.
Oh, wonderful.
So if it's clear, you'll be able to see it in person. All right.
Chris, just on the original stream.
I said Friday, didn't I?
Fridays,
Yes.
it is Saturdays.
It's Saturdays, yes.
Saturdays, yes.
That's my brain knowledge. I forgot to change it.
Yeah.
Thank you.
Well done.
When I said it, I thought that doesn't sound right. I don't have a website report, and I don't think there's anything too much happening there, and Michelle isn't here this evening. So just a reminder then, upcoming events, the top one there is Saturday evenings.
We don't have anything on the screen.
So. Oh, no. Oops. Now it's decided to stop working. Okay, well.
Unplug the middle end again.
Yeah, so here, maybe I can get it in all. Yeah, let's try that. Okay. So the top one should be Saturdays for the active observers. Everything else remains the same. We will try for the UVic Observatory this Friday. And I think that's it. Are we, anything else? Did I forget anything else? Okay. So let's switch this over, I guess. And
Okay.
all right, see what we can do.
So, do you want to help Wendell get his thing connected?
Yeah.
Yeah. What do we push here?
You just turn off the blank. Yay, that was cool.
Okay. Okay, folks, about a year ago, I connected with Wendell Schuster when I was writing an article on the Charton project, a new radio telescope in Penticton. And at that time, he sent me a list or a file with a whole pile of slides about a talk about supernovae. And I looked at it and I said, wow, we got to have him down here to see this. I think we got a treat in store tonight because it was spectacular. A little bit about Wendell. He joined RASC in Vancouver in 1980 and he's been a continuous member ever since. And he's been in Penticton area since 2000. He got his start very early on in astronomical outreach. His first show was in grade 6 when he gave a talk to the grade 2 class in the school. So he knows how to deal with tough audiences, although Luke does in good shape here. He's been a very active member of RASC in the interior. He is the tour guide for the Dominion Astrophysical Radio Observatory in Penticton. And he's going to give a short talk on that and then a longer talk on historical supernovae. He's been very heavily involved in all sorts of executive for the astronomical associations in the interior. He's given numerous long talks, and he did say to me, Reg, you haven't been to one of my talks. He goes a bit long, so watch out. The one other interesting thing is that I don't know many other astronomers, professional or amateur, who have 1,872 glass plates from the original Palomar sky survey in their basement. But Wendell does. And I think that shows you his focus, and I think we're in for a real treat. So I'll just pass the floor over to Wendell and take her away.
Yeah. Okay. All right. Anyways, I do tours at the Dominion Radio Astronomical Observatory, and a lot of times when people come out and just come and introduce themselves to me over there at the visitor center, I'll ask them, how much time do you have for a tour? And a lot of people who don't really know too much about astronomy and want to get interested in astronomy might say about 20 minutes, 30 minutes. And the next thing I know, I'm doing tours for about 2.5 hours to 3 hours. So I'm just going to let you know that my talk here is about 20 minutes long. So, and we'll just start with this. So I do the tours here. I've been doing this for about 14 or 15 years now. And a little bit about the observatory itself. It's operated by the National Research Council, just like the Dominion Astrophysical Observatory up the street here. And the hills surrounding the White Lake Basin in this area offer protection from all man-made sources. And a lot of people that come in will have their cell phones turned on, and if they put them in an airplane, we'll be thinking it's okay, but actually, we want to keep the site as pristine from radio signals as much as possible. And because of the mountains that are ring around the observatory, it is ideal for doing that kind of research. And a little bit about radio astronomy. A lot of people think that radio waves are just sound waves, but really, radio waves are like another color of light. And it's a study of naturally occurring radio emission from celestial objects. And radio waves are, like I mentioned before, are like invisible colors, roughly between 500,000 and 1 million times longer than physical light. So we really don't know what color radio waves look like, but it would really help if we had eyes that are about 700 meters in diameter. Everything would be good. So they provide an alternative view of the sky that otherwise cannot be obtained. So we can see through dust clouds and things like that. So this radio picture that you see here, it was generated from the synthesis telescope. I call them the 7 doors because there's 7 antennas that are out there. And our solar system resides inside of what's called the Cygnus Orion spur. It's part of the smaller arm of the main Sagittarius arm. And basically what we're showing you here is that space isn't completely empty. It harbors all kinds of continually evolving stellar birth and death events out there in space. And here's the seven dwarfs, the synthesis telescope. The first thing that you're going to encounter is this telescope when you're walking along. I think it's about 600 meters until you get to the visitor center. And also, what's not shown on there is that I came up with a new exhibit called the timeline. Reg, did you see the timeline last year?
No.
It wasn't built. I mean, it wasn't painted at that time. But it's 691 meters long, and each foot on the timeline is supposed to represent 6 million years. So it's quite a long timeline. It also shows a whole bunch of different eons that have taken place during our history of the Earth and the universe. And one of the big things that you'll notice is this big orange line that goes along the top end, and it's supposed to represent the amount of time, amount of space and time where China's going to be studying the universe. China's new telescope that they built here on site. It's called the Canadian Hydrogen Intensive Mapping Experiment. And it's going to be making the world's biggest three-dimensional map of the universe. So I'm going to show that to you in a moment what the telescope looks like. So the thing that made the synthesis telescope so famous is that there's 7 antennas arranged over a spacing of 620 meters, and they capture radio waves and they're instrumental for the Canadian Galactic Plane Survey, which is become an international effort to map the entire Milky Way galaxy. And for the most part, we've covered the areas from Orion all the way down to Vulpecula, Sagitta, and the outer part of our galaxy in between that. And this is the world's most detailed radio atlas of the sky. The 22 megahertz is another telescope. This is the only one that doesn't function anymore, but it is Canada's largest radio telescope, or largest telescope. It covers 65,300 square meters. And it mapped galactic emission features as well as quasars and vast star-forming regions in the Milky Way galaxy. And shortly after the discovery of quasars, we're just a few months too late from actually discovering quasars, but I guess you could say in radio astronomy, getting a silver medal isn't that much. But what we see here is that when we looked at quasars and galactic point sources, we found as we go to lower frequencies, which is redder colors, if you want to think of it that way, these point sources and quasars get very, very bright. So that's what the main interest was at that time, to discover how bright these objects really were. The John Galt telescope was the first telescope that was built at the observatory, and currently is observing, there's in between 2 programs where we're studying the magnetic fields of the Milky Way. And the reason why they're interested in studying the Milky Way is because magnetism actually promotes or actually decelerates star formation depending on its orientation and where the gas clouds are in our galaxy. And also what gave the telescope its prominent fame is that it was the first telescope, including another one in Ontario that we used to have 2 radio telescopes at one time, were used to connect together 2 antennas. This is a technique called interferometry. But these 2 antennas were 3,074 kilometers apart. And this technique called very long baseline interferometry was headed by John Galt's team, and they were given the IEEE award for doing this achievement because it's affected us in so many ways regarding astronomy and earth science and geodesy. So the Galt telescope, there's another feature in landmark that I'd love to show you guys if you come out. So the 10.7 centimeter solar flux monitor station is the most widely piece of astronomical data in the world. I mean, well, I guess I could argue almost the world, just because this is the longest running solar index that we have of radio emission, of any type of emission, besides sunspots, but sunspots don't measure emission. And this monitoring station's been looking at the sky for about 71 years at the sun, and we make 3 official measurements of the sun every day. And you can download this if you go on spaceweather.gc.ca and get all 71 years worth of data if you want. But if you don't want to do that, I've got information at the visitor center, and that'll show you the charts too. So that all comes part of your package when you come in. And I know Reg is very interested in CHIME, and I kind of put this little clip in here just for you, Reg.
Thank you.
Okay. So CHIME is Canada's newest radio telescope. It just opened last month. And CHIME's key science is to map the large structures and to measure the expansion history of the universe. And secondary science will include measuring cosmic scale gravitational waves by studying the timing of pulsars, and also to study fast radio bursts. So those are some really key science programs that are going on that nobody has done before. And I'm looking forward to the results in a couple of years. On September 7th, we had our science minister, the Honorable Christy Duncan, inaugurate CHIME. She put the last piece on there, and she gave a little talk about science in Canada and how everything's being forwarded from there. A little bit about CHIME itself. Oh, good. You guys can see the mesh on there, right? I was trying to get that on the camera when I was taking these pictures. But radio waves, actually from cosmic sources, will reflect off of this mesh. Even though you and I can see through it, radio waves can't. It will actually reflect off of there. And then,
it's right there.
Perfect, thank you. Okay, so the radio waves come down, they reflect off the mesh, and then they will get focused at some of these antennas here. And there's 256 antennas that are dual polarized, meaning that CHIME here has four cylinders. Okay, so you can see the 4 cylinders here, and each one of them has 256 antennas on it. So there's 1,056 antennas, sorry, 1,048 antennas along here, and then 2,096 inputs, because there's a polarization going this way and a polarization going that way. So so each connection from the antenna from here, the antenna goes into the telescope's, what we call the F engine, where there's a whole bunch of field programmable gate arrays there. And each one of these antennas is attached to a cable that's 50 meters long. So that means there's about 102 kilometers of coax cable connecting the antenna to the telescope. And they all have to be the same length, because we want them, all the timing from all these signals that are reflected by the telescope to arrive at the telescope at the same time. And this is what it looks like inside of the telescope. This is the FPGA, Field Programmable Gate Array based F engine. And this is Tom Landecker. He's been one of the scientists that have been working at the observatory since 1968. He really knows his stuff there. And he's one of the, he's both a radio astronomer as well as an engineer. He knows everything inside out. You want to know anything about the observatory, you ask him lots of questions. And so Tom let me in to take the photograph of all the connections. So what happens is those cables, those 50-meter cables, they come into this point here where they're amplified, and then they're digitized inside of here as well. And then from there, these signals are digitized to what's 400 kilohertz resolution. So 400 kilohertz times 1,000 channels works up to a 400 megahertz spectrum where the telescope's going to be looking at the sky with. So hydrogen comes to us at 1,420 megahertz, which means that if you're looking at this, at radio waves coming from this hydrogen that have been redshifted because of the expansion of the universe, then 800 megahertz means we're looking about halfway out into the universe, and 400 megahertz is about 4/5 of the way out to the universe. So this is how CHIME's going to map out this expansion of the universe itself. And from the F engine here, all the way to the, it goes into another trailer where the the digital signals come in here and they get processed by a whole bunch of graphical processing units. And these graphical processing units is what made the telescope cheap enough so that us, the taxpayers of Canada, can afford to build a telescope like this. The telescope has no moving parts, but these GPU units came down so much in price because of everybody that plays video games have helped promote that. So my son, Al Shane, is one of those that love to play video games, and I salute him because he's helping these graphical processing units down so much in price, so that this computer could be built. Now, what happens is once the signals get processed through here, they get, after they've been digitized, they get processed, and then the correlator, which is kind of what this engine room is all about, writes everything to the data to disk for later processing into sky maps and maps that I was telling you about. And when it gets written to disk, it goes into another building that's at the observatory, and it's got to be processed, and the reason for the processing is to reduce the amount of data. CHIME collects about 1.6 terabytes of data every second. So, and if CHIME's going to be studying the sky for 5 years, that's 220 million seconds, and multiplied by 1.6 terahertz, we're looking at about 300 exahertz worth of data, and that's got to process all of that. So what happens is CHIME is going to be reducing that data by multiplying all these signals together every day as the Earth rotates, and it's picking up on all of that. And so after all these hard drives get filled up every week, they're going to be sent off to the University of Toronto by truck, because it's too expensive to send it by fiber optic. So anyways, that's a little bit about CHIME. And you can see here, I'm showing you the power unit that they have here. This is just one power amp station. 1,600 amps can be processed through here, and another 1,200 next to it. And the CHIME uses 250 kilowatts of power to operate. Most of that's to feed those GPUs that we saw there. So the X-engine room is kept to refrigerated 45 degrees. I put that in quotes because that's not cold, that's actually very hot. And there is some concern that because of those temperatures, those GPUs might not make it for 5 years, so then they're going to try to refrigerate it even more. But for the most part, we only have to worry about that during the hot summer days when it only goes to 40 degrees at the observatory. 40 Celsius, not Fahrenheit. And the GPUs, they're internally cooled with water and a small amount of ethylene glycol as well. So they're actually kept cool on the inner part. And this is the fan unit that we have here to help blow up all that excess heat from inside those trailers. Now, when you come to the observatory, if you come and see me, I'd love to come to see all of you guys and come out there. And this is where you meet me, and this is where I will custom tailor your tour based on whatever you're interested in. If you're interested in pulsars, we'll talk about that. If you're interested in the sun, we'll do the solar hub. If you're interested in talking about supermassive black holes or whatever your interest is, we'll talk about. If you want to talk about observing, we can talk about that too, or which telescope to buy. Whatever you guys want to talk about, that's what we'll focus on. And that's how sometimes my 20-minute talks end up being about 3 hours. So this is what it looks like inside the visitor center. I've had 25,000 visitors that I've talked to over the past 15 years, and I keep stats on every person that comes in. I don't take your name or anything like that, but I have to keep track of the numbers that come to the observatory. And so there's lots to talk about when it comes to astronomy and radio. And I like to talk to people about optical astronomy and compare it to radio and explain to you why we need both to really understand the astrophysical processes. And outside of the visitor center, if it's a nice sunny day, we have the Celestron C8 with a Bader filter on there. It just makes the sun look like a white snowball, I guess you could say, with a couple of freckles on it. We also have a hydrogen alpha telescope that I just kind of earned as like a long-standing achievement award. I've been there for about 10 years, and I guess after the government changed, we were able to get some funding for this telescope to show everybody when we came out. And then the other telescope that you see here is a radio telescope, and I'll show you how a radio telescope compares to an optical telescope when you look at the sky. And over here, we have stuff for the young visitors who want to come out and see the solar system exhibit. I'll talk about Bode's law here and talk about why Pluto is or is not a planet. There's a big discussion on that. I need an hour just for that. And then over here we have the whisper dishes that you can talk into, and there's the timeline I was mentioning to you about earlier today. So other things that we can share. Is that it? Okay. So and some more information I can show you too is some of the big projects that are going on, the technical things that the engineers are working on. About 3/4 of the staff that are at the observatory are actually either computer engineers or engineers that develop radio astronomy devices and instrumentation. So there's lots going on there, because you can imagine you can't really go to the Walmart and pick up a radio telescope. So there's lots of very, very specialized staff that work there that are part of ongoing research that involves other countries and other radio telescopes. So, so this is my invitation to you guys to come see me. It's okay. So, like I said, 30 minutes to an hour. That's the general way I try to work myself towards. And it can be a bit of a walk, so especially when it gets really hot out there. Drink some water and don't leave the pets in the car. I'm more than happy to take the pets on a tour as well. And most of the time on the weekends, I'm there between between 10 a.m. and 5 p.m. on weekends and holidays. And I have one more weekend, extending one more weekend this year. So we also have the scientists give tours out between 2 and 5 o'clock on Sundays in July and August. So if you pick my brain too hard, then you can pick theirs and really ask them some really good questions as well. And hopefully I'll be able to inspire you to ask them lots of hard questions, because that's what I like to see. Anyways, we're 24 kilometers south of Penticton, so if you do want to come out that way, I'm more than happy to show you around. Anyways, any questions on the tours out there? Yeah.
I was just asking that background.
Oh, okay, go ahead. Any other questions?
You mentioned some of your items you have.
Oh, right, and so I brought a whole bunch of toys out for you to take back with you. We have some periodic tables. We have some FAQs about the observatory itself, and some more information. I know the DAO has their own brochures that look very similar to this. So if you have one of these with the DAO, then just make sure you've got the radio one as well. If you want to know more about my tours or the tours that are given out at the observatory, this is all the information that you need to know on how to get there. And we also have some information on Chime. And I'm just gonna leave all this here for you guys to take that with you, so you guys can keep everything.
Before you go on to your next talk,
Yeah.
How are people hearing? Can you hear back there okay?
Yeah.
Okay, good.
Okay.
Great.
All right. Are we ready for the next one?
Yes.
Okay. So I'm going to do the main talk right now, and let me just jump out of here and go on to this one. Yes.
The 22 megahertz.
That's right.
Were the point source. Right.
Yeah, they're like what the astronomers call that kind of radio emission. They call it discrete radio sources.
And it's not working now. Like it's not.
And it hasn't been in operation since 1973.
Okay.
So what had happened was in the 1960s, just after the telescope was built, it was built from 1964. They observed the sky between 1964 and 1969. This was during that solar minimum. If the sun gets more active than that, then the charged particles that come from the sun actually block out, stop the radio waves coming through the ionosphere. And so solar maximum is not the best time to use really low frequencies to observe the sky with. So what they did was they looked at the sky at that time, and then there was another astronomer writing this thesis just after the solar maximum, and they kept the project going for about 4 years after that. And then after that was all done, the copper price skyrocketed back in the 1970s. We went through all that inflation and everything, and they took everything down, and that's why it doesn't exist anymore.
So is somebody else doing something like that in a different way somewhere else?
There's a telescope project called LOFAR in the Netherlands that's doing something similar. But for now, all of the information on the 22 megahertz, I have a map in the visitor center. I can show you it's still state of the art even after 50 years, or almost 50 years. But right now, LOFAR is doing a survey of the sky. They're doing something similar to what China's doing. They're actually going even further back into time, looking at that hydrogen when the universe is almost probably at the time where the first stars had started forming. And their project is to map that out. So, you know, so this is still state of the art for now. Yeah. Any other questions? Yeah.
We're out there in summer, but the wife and I, there's another one there too, look like a T with all these wires.
Yeah, that's a 22 megahertz telescope.
Now, I noticed that where the wires come together, it's called the bird's nest.
Oh, that one. Okay.
There's a bird take off.
Okay. Okay, that's okay. Part of the tour as well. Okay, one really interesting thing about that there's a bit of a story behind that. Do I have time for this?
Oh, it's probably the carry on.
Okay. All right. So what happened was back around 1995, there was an engineering student that was working on his doctorate, trying to get some information on where he could pick up stray radio signals and pinpoint to their location or their origin. And so he built his tower, and he ran out of funding to finish it. He promised he'd come back. We left the instrument up there for him. And in the meantime, while he's trying to get his funding, the Osprey came in and started building a nest on his work. And so the Osprey built their nest, and they bred and they laid eggs. And even though to you and me that might not sound too exciting, it was very exciting for the biologists at the time. And the reason for that is because in the Okanagan, they used to spray all the crops with DDT. And so there's about 25 years where there were no osprey reproducing, and that was the first place that they started to reproduce again. And now all throughout the Okanagan, you can see the osprey nests everywhere along rivers. So that's a little bit of the story. So I always like to quip that, that individual's research project kind of went to the birds and, where he is now. So maybe he's biologist now, I don't know. Anyways, I'm going to start my talk here on historical supernovae. And the reason why I chose doing this talk is because this is one of the last things I show you guys on the tour. I show you a great big panel of the world's most detailed radio atlas of the sky. And I often wondered that when I showed everyone this, what did people see when they saw these supernovae? So, or these events that would take place, and what did they think about it? And how do we know that they actually saw it? And so here's a supernova remnant here and a supernova remnant here. Here's another one that's much younger. And this one's one, but I'll talk about that later. This one's another one. So there's a whole bunch of them peppered all throughout our Milky Way. And this talk is basically about the study of new stars appearing in the sky that are so brilliant that they can be seen even in the daytime. And so this presentation is called Historical Supernovae. Supernovae are rare astronomical events that definitely would have had influence on sky watching people at the time who witnessed them. And this rendering that you see here is supposed to be an artist's impression of what a birth of a supernova looks like. Progenitor star, this is from a type 2 supernova, ends its existence becoming a supernova brighter than an entire galaxy. And so the areas that you see that are in white here are the actual explosion of the star. The orange portions are gases. They're a little bit cooler. They haven't been heated up by the actual explosion yet. And the yellow colors that you see here are fragments of the stars that are cooling while the gas gets heated rapidly. Now, I have to put an asterisk up there. As I said, all observed supernovae in the Milky Way occurred before the invention of the telescope. And there's probably those of you here who realized that there was a supernova event that was visible in the year 1987. And I excluded it from the top because it's not the Milky Way. It was actually in the Large Magellanic Cloud, which is a satellite of our galaxy. But looking back at the other historical records that we have of supernovae in the Milky Way, there's four main ways that all of this has been recorded over our history. And the four ways are through verbally, from generation to the next generation. Then there's there's markers of these what may be supernovae in stones. Even in rock art, we see similar events as well as the written records. And the written records are still require a lot of interpretation to go through that, because the ancient observers did not have the knowledge of what supernovae were, and therefore careful consideration had to be made, followed with modern day telescopes and observations to verify that's what they actually seen. So starting off with verbal communication, transient appearances of objects have been seen in the sky, things like comets, meteors, eclipses. All of those were recorded orally by other cultures. And it's also very likely that supernovae in the distant past were also recorded and made as well. But there's nothing that we can identify with the modern events, except for something that was seen in 1843. It was recorded verbally by the Burunk culture in Australia. And this event is something like a supernova, but not exactly a supernova. Eta Carinae still exists, it hasn't blown up, but it's extending its shell of gas back out in space. And when it does that, the hotter part of the star brightens up quite considerably. And it's seen quite easily and has been recorded from generation to generation. Identifying clear examples is very challenging because oral traditions give ambiguous information about the supernovae. And verbal passages are also open to interpretation. So everybody might think of their own ideas of what they might be, or to the best of their knowledge, and then you read it and you might lose the information from that. And also, I wanted to show you guys a tapestry over here. I'll give you an oral tradition here of what this tapestry represents. And so you can see over here, there's a path of what looks like a river that's supposed to represent the Milky Way. This is done by a culture called the Yolngu culture in Australia. And they believe that after a person's death, a canoe called a larpan comes out, and it takes them into the dark recesses of the skies of the Milky Way, in these, what we call today, the coal sacks, the dark nebulae that are out there. And then so what happens is when a person dies, they're taken to an island in the Milky Way, where countless campfires are seen along the Great River. So here's these campfires along the edges of the Milky Way here. So that's what that represents. And when a meteor streaks by across the sky, the canoe returns and signals to the family of the loved one that has passed on that they arrived to the spirit world. So that's kind of some of these oral traditions here that get passed on. Now, some markers in stone. We also have, in 1981, there was an archaeoastronomer, his name is Peter Burden, who speculated that this bicycle wheel that you see here depicts a supernova event. And these designs are found all throughout Australia, and there's 2 petroglyphs near Sydney, New South Wales, where a crescent moon and a bicycle wheel design can be seen, reminiscent of rock art that of Chaco Canyon, believed to represent the supernova of 1054. So I'm going to show you that the Chaco Canyon rock art in a moment here. Another marker in stone that's been recently discovered is in Mexico, and was recorded by the Chalchihuitania culture, depicting the supernova of 1054, and it was witnessed by at least a half a dozen cultures around the world at that time. And most recently, an astronomical marker was discovered at ancient Mexicans known to witness and record a supernova event. Now here we're going to the rock art part of the talk here a little bit. The rock art has been interpreted to show the crescent moon over here and the supernova of 1054 over here. And the handprint signifies that this is a sacred place, as well as that the fingers that you see here point to the direction of where the event was sited at Chaco Canyon. Now, another event that took place in 1054 shows a pictogram that was made in the American Southwest by the Anasazi. And the date of this pictogram that is shown here can be seen here, but it doesn't show the actual date of the supernova detonation. It just shows the date of when this was all painted together here. And here's the moon with the supernova next to it as well. And that was actually, this event here was actually believed to have taken place on July 5th in 1054. So that's about 1 day after the big event, the big detonation had appeared in our skies. And some more rock art, that depicts a much brighter supernova, was witnessed a half century earlier, called the supernova of 1006 or 1006. And this rock art is the only known record of the supernova 1006 recorded in the Western Hemisphere. So it was discovered about exactly 1,000 years later at the White Sands Regional Park, previously occupied by the Hoboken culture between the years AD 500 and AD 1100. So that's pretty much at the height of their culture there is when they recorded that very, very bright supernova. Now we'll go into written records. There's 4 different types of written records that we can go back on our history with. One of them goes back to the time of the European monasteries. They had chronicled two events, well, two different places of the same event. And the Arabic also had chronicled supernovae of around the 10th century, 11th century as well. And then we also have the Far Eastern histories that are very, very extensive. They go back to 3 millennia. And post-Renaissance European scientific writings, we'll talk about those in more detail as well. So first of all, we'll talk about the medieval European events that were recorded. 2 monasteries recorded supernova events during the Middle Ages, and likely reasons that chronicling new stars held little regard by the Middle Ages Europeans is because the knowledge of the sky was poorly understood. People didn't really know the names of the constellations. All of that was brought by the Arabic culture around the 12th century. And if new stars did appear, it didn't seem like it was that important to the masses, to relate to the masses by the churches. And also supernova 1054 that we talked about earlier was not written down anywhere in any of the monasteries, possibly because 12 days prior to the supernova going off, there was a major event going on where the Roman Catholic Church is split apart into the Orthodox and the Roman as well. So, and also, it was believed at that time that if God created the sky, then the sky must have been perfect. So being imperfect might not have been an option. They might have kept it quiet. We don't know. So supernova 1006 was the only supernova that was recorded in medieval Europe, and it was only visible south of latitude 47 degrees north. So even from Victoria here, we would have had a very difficult time seeing it if we were around 1,000 years ago. And the reason for that is just because it was in the constellation of Lupus when it had detonated. So some more written records go back to the days of the Arabic days, where we see that there's some text that are here that designate where supernova 1006 took place. It was written in Abu Ibn Sina's book, Al-Shifa, published in 1007, which talks about all the enlightenment that was accumulated up to that time, and not only included astronomy, but a whole bunch of other scientific disciplines at that time. And so it was recorded by Arabic observers, and to date, there's no subsequent supernovae that have been uncovered by that culture after that. Okay, now the Chinese have a very colorful history. So in the Far East, we had, the emperor had employed astronomers and astrologers, okay? And what happened is that there were 5 astrologers that would be employed that would watch over the sky just outside of the emperor's palace. And there'd be one astrologer looking to the north, one looking to the east, one looking to the west, to the south, and one that had to look straight up. I wouldn't want to be him. And they would record all the events that took place, and then they had to interpret what they were actually looking at. And all those interpretations that the astrologer made up would have to be was based on where this event would appear or disappear in the sky. So the astronomers themselves, their main task was to keep track of what day it was. That was their main task. I don't think their history is as colorful as the astrologer's history, because if the astrologer got one thing wrong, well, it wasn't the best thing that would happen to them. But we have detailed records that go back to the time of the Qin dynasty, 2,200 years ago, and then after the Koreans and Japanese had started their own societies around the 7th and 8th centuries, then they used the same kind of, they even used the same language as the ancient Chinese, as the classical Chinese, as well as determining what kind of stars they were looking, or objects that they were looking at, and basically in Chinese, classical Chinese studies, the cosine stars here were considered as your guest stars. Those are the most likely ones to have supernovae as a result of what they were seeing. The other objects, like the cosine stars or the Huising stars, were more likely to be comets or variable stars. So a lot of astronomical records suffered considerable loss of detail because they were mere summaries of a long dynastic history covering centuries of archived text. So what they used to do back in the Chinese culture is that the astronomer or astrologer would record the observations that they had made, and then when the emperor had passed away, the official historian would actually summarize the event that would take place. And if the dynasty disappeared, then they would rewrite the history of why the dynasty died and how the new dynasty was much better. So they had a really, really colorful way. But because of that, we still have a history as to these events that can be seen. So this is what the Chinese star maps looked like. It was uncovered by the Jesuits, and they had just copied them, what they saw. And the sky is divided into 283 asterisms. Now, I don't say these are constellations because we know there's 88 official constellations out there. But 283 asterisms, or kind of like an asterism, is like the Big Dipper or the hockey stick. You guys know about hockey stick asterism? Who here knows about hockey stick? Awesome. Okay. So I'll show you some of the constellations that I recognize that are on here. This here is Orion. So this is the southern hemisphere sky. This is the northern. So there's the belt stars there. There's Rigel and Safe. And you got Canis Major over here. And then on the other side of the sky, Orion's up here. So you got Betelgeuse there, and Bellatrix there. And then Cassiopeia is here, and the Cygnus and Aquila over here, just to give you a reference as to what we're looking at. The astrologer's duty was to determine the kingdom's future course of events. So the celestial sky was actually divided up into 28 lunar mansions. And there are asterisms which are aligned with the mansions. The mansions kind of followed what we call the ecliptic, but also followed the celestial equator as well. They didn't define it like the way we do. And there's 28 lunar mansions. One's supposed to represent each day in the lunar calendar, but we now know there's 29.53 days in a lunar cycle. So if there was an event that had occurred in a certain asterism, as being in a lunar mansion, even though it might have been way up in Cassiopeia, so they might have recorded. Okay, so Cassiopeia would be about 0 hours, so they might call Alrisha, which is Alpha Pisces, Pisceum, as the main star in that lunar mansion. But if the event happened in Cassiopeia, they would say that this event happened actually in Pisces. So it's a little bit confusing. There's a lot of interpretation that has to be considered when they try to figure out, if a supernova event actually occurred at a certain time in a certain place. And sometimes, if they were recorded in the appropriate asterism, they wouldn't mention which star was nearby. You'd have to look using other observations to look for a supernova that could be in an area that's 100 square degrees in the sky, because an asterism could be that big. And take a look at the Big Dipper, right? The Big Dipper covers the whole range of sky. So it'd be like me saying, oh, I saw this bright object a few years ago in the Big Dipper. And you might wonder, well, where exactly was it? So if you wanted to study it, then it would be a lot harder to do that. Astrologers would also categorize their observations as into 9 different categories, including thunder and lightning events, eclipses, sunspots, lunar events, planets, conjunctions. So conjunctions where 2 planets kind of come really close together in the sky, meteors, meteor showers, aurorae, and guest stars. And the guest stars is what we're very interested in. And so it was the astrologer's duty to determine what the kingdom's future would be, because if the event that they saw a planet going to, say, a lunar mansion, then any natural events would affect the people, but non-natural events would affect the emperor. And they had to determine what the fate of the emperor would be. Because if the object would disappear in a certain asterism, then it could mean that there might be an assassination or a loss to the emperor. And it was up to the grand historian who wrote the event, the next dynasty, or the next, after the emperor's reign had ended, it was up to him to make sure that the astrologers' predictions were met with success. So sometimes you get a little bit of a difference in history over here. Anyways, this here's the oldest known observatory. It was built in Korea around the year 647 for the Queen Songdok. In China, observatories were placed just outside of the emperor's palace. And in the 7th century, the Tang dynasty and the Silla ascendancy in the Korean cultures adopted the classical Chinese system of documenting their history. And they even used the Chinese language at first to write down their observations. But the Koreans got to be very accurate with their descriptions, and in the 15th century, we have very, very detailed observations that were made by them. And the historian needed, in both Chinese and Korean kingdoms adopted the classical Chinese system of recording history. So this here is a record for the supernova of 1054. This is what you have to read and interpret to know that we've seen something in the sky at that time. And the Chinese would make their observations and record it based on the day of the emperor's reign. So this is how we know exactly what day these events would occur on. But we don't have any recordings of any supernovae by the Koreans until after 1452. Okay, now the European astronomers, you may be more familiar with them. In 1572, Tycho Brahe was a Danish nobleman who had actually looked up at the sky and made very, very detailed notes. The brightness of this object, this new star that he saw. He reported the color, the duration, how long it stayed visible in the sky for. And one of the biggest things that he recognized on here that really changed the paradigm at that time was knowing that the new star was not in our solar system, that was much further out. And that also means that the sky is not perfect. And at the time in the 16th century, the state was the church, and the church had their ways of making you think that the universe must have been perfect as well and unchanging. So Tycho had published a book in 1573 called De Stella Nova, and he coined the term nova, meaning new star. And some people might argue that's something that doesn't run very well on four wheels. So, but some might say they're good cars too. So, another based on we had Johannes Kepler looking up at the sky at the next supernova event that was seen in year 1604, and just like with Tycho Brahe before him, he also noticed that this star did not move in the sky and it is not part of our solar system. So he made notes of that as well. And he published a version of kind of Tycho Brahe did back in 1572 and 1606 on his book called Stella Nova. Now, this one here was quite an interesting one. I'm going to make a little argument here for you guys. I'm going to say that maybe John Flamsteed here might have discovered a supernova without even knowing it. Back in the 1600s, around the 1680s, John Flamsteed was looking up at the sky and he was cataloging all the naked eye stars of that time. So what he would do is, let's say Cassiopeia had 103 visible stars. He would classify the first star that was seen in that constellation. It would be the westernmost star. He'd call it one Cassiopeia. And then the next westernmost star would be two Cassiopeia. The next one would be three, and so on. So, what he had cataloged was 2,919 stars in his atlas, and he had found this star called 3 Cassiopeia that he observed. It was a very, very faint star. It was almost mid-6 magnitude. And he observed it once in August 1680, and then it was never seen again after that. And two reasons could be is that one, it might have been a supernova, which is my argument, and the other one might have been an error in his observation recordings. The brightest radio source in the sky is called Cassiopeia A. So 250 years later, this object was discovered with a radio telescope that's within 10 arc minutes of where he positioned 3 Cassiopeia. And so 10 arc minutes is like a sixth of a degree, a very, very small angle. And it's when they study how Cassiopeia appears to span in the sky, it appears that this supernova here may have detonated around the year 1667. That's our best guess as to when it had detonated. However, Flamsteed, it might have detonated in 1680. And the reason why we didn't see this as a very, very bright event like the 1572 or the 1604 supernovas is because this radio supernova remnant is in behind of a huge dust cloud that obscures light. So it's probably been dimmed by interstellar dust by a factor of about 11 or 12 magnitudes, which would be about the right amount for that amount of dust that's found in that part of the galaxy. So it's possible that maybe Flamsteed actually did see that supernova. If he did, he would be the only person on Earth that didn't see it. And nature, not history, has hidden most supernovae. Our galaxy, the Milky Way, is oriented in such a way that it's a pancake from where we are. And due to our point in space, interstellar dust obscures most, if not all, the visible light of the stars in the galaxy. So that means that you could say that there's so much dust in our galaxy. That's one of the big reasons why it's dark at night. So if you're scared of the dark, you can blame it on the dust, because all the dust is small up here as well. Okay, and here's a list of the recent supernovae that I just talked about here. The 1006 event was the brightest one. This is in the last 1,000 years. We talked about 1054 being the supernova where it was seen in Chocolate Canyon. I didn't tell you about 1181 yet. I'll tell you a little bit about that in a few minutes. But you'll notice that most of these supernova events take more than 40 days. They take like about a year to be seen. And I put 1680 as a question mark. That's this Flamsteed one that we see here. So I'll talk about these ones in a little more detail right now. So supernova 1006, this is an artist's rendering of what they think that supernova would have looked like. If you're in the southern Mediterranean, you're looking at Lupus there. This object would have been as bright as a first quarter moon, but it has a pinpoint of light. So what the artist did was he took a picture with the first quarter moon in the way, with the ocean in the background there and superimposed it on parts that where Lupus is to give us that effect of how bright that object would have looked in the sky's background. And this is the location of the supernova 1006. Those of you who know your constellations really well, it's in between the Centaurus and the Lupus border. There's the star Antares that we can see in the middle of summer, very low in our sky. And that was its position. That's why we probably would never have seen it from here if we were around 1,000 years ago. This is what supernova 1006 looks like if you include X-rays, radio waves, and optical. Now, optical, the only part of the supernova that you can see today using an optical telescope is this yellow shard here of information. But if you combine radio and X-ray data together, you can see a very, very nice bubble of material that's been expanded out from that. Okay, so this is a composite view of the supernova 1006. And in 1054, this is what the supernova would have looked like. It was estimated that it was as bright as the planet Venus, if not a little bit brighter. And there's a crescent moon that we saw back in the Chocolate Canyon rock art. And that's the artist's impression of that supernova on July 5th. So this supernova, the Crab Nebula, which is now associated with this supernova, is about 6,500 light years from Earth, meaning that the light that's coming from there takes 6,500 years to get to us. Okay, here's the location of the Crab Nebula. Those of you who got your Messier certificate would know that it's just off of the star here, Zeta Tauri. So right in the middle of the galactic plane here, where the Milky Way runs right through, is where that supernova is visible. And also the Lupus supernova here is also right in the galactic plane as well. That's where these supernovae tend to occur at. Down here we have an image of what lights up the supernova. This is the Kraft pulsar, which is the rightmost of the two stars here. This one is the generator of all this light that you see in here. The blue glow is the visible part of what we see, and the glow comes from electrons that spiral through that nebulous magnetic field. And the supernova is actually centered in the Perseus spiral arm. Now, I'll talk about supernova 1181. This appeared close to the star Eta Cassiopeia, which is this star here, at the very end of the Tierra of Cassiopeia. And just like the Crown Nebula, this remnant has a filamentary structure all throughout the nebula, as well as a pulsar that's spinning 15 times per second. And this is what an X-ray picture of the supernova 1181 looks like. And this remnant here that was imaged by the Chandra telescope, showing the central pulsar, which is here, and a torus of X-ray emission. And so further out, X-ray loops can be seen as a very, very hot active nebula that tends to be pushing material all throughout the interstellar medium. And it too is in the Perseus spiral arm. That's the next spiral arm that's out from the one that we're in. And Tycho star, this is in 1572, its location that you see here. Again, it was as bright as the planet Venus. 1181 here, I didn't know how bright that one was, but that one's brightness was approximately that of the dog star series, which is the brightest nighttime star at minus 1.6 magnitude. Okay, supernovas 1572 can be seen up here, and it looks like it's kind of associated with the star-forming region that you see here, but it's not. Both of these are about 3,500 light years away from each other. And, 1,500 light years apart from each other. This was 3,500 light years away, and that's 5,000 light years away over here. And Tycho star, this is what it looks like if you look at it both in X-ray, color, and infrared. And the X-rays are the blue colors that you see here. Infrared is the yellow, and I believe it's yellow, and the red is the visible light image from that supernova remnant. And then this is the location of the supernova 1604. What's really interesting about that supernova is that you have Mars, Jupiter, and Saturn plus a supernova all forming a line in that. That would have been quite a spectacle to see that in the 1600s. I love watching the planets dance in the sky. So that would have been really neat for me to see that one. And this is the location of the 1604 supernova. Again, it's right in the middle of the galactic plane. Seems to be something that we see all throughout the supernovas here. And this is one that was recorded by the RASC at the time. So in 1604, at Kepler's star here, you can see the remnants of that star still exists here in visible light. And the bright knots are these dense clumps that form behind the moving shock wave, and as it plows into the stellar wind, it actually gets swept up in the electrons, and you actually light up the nebula. So, the shock waves is where the high density material is actually meeting up with the lower density stuff. And this is what a composite view, including X-rays, optical, and infrared put together give us a picture of what the supernova 1604 looks like. And remember, in yellow here, this is all we see in visible light, so we don't see the entire shell unless we use the entire spectrum on that. But again, you can see that these supermassive stars that have been blown up are pushing material back up in space again, and eventually this stuff will become the dust that we saw back up here, that obscure the other supernovae. So here's that dust that you see here in all these patches of the plane of our galaxy. So now in 1680, I'm going to say 1680 with Cassiopeia A. This is Cassiopeia A's position in the sky, and This, again, might have been the one that Flamsteed saw from the star 3 Cassiopeia. If this star really was a supernova, it was almost invisible to the eye. And if they could measure how far away it was at the time, they would determine that it's about 11,000 light years away, meaning that this object would have been about magnitude 2 when it detonated. So if there was no dust clouds in the way there. And again, you'll notice all these supernovae are right in the middle of the galactic plane as well. Okay, so this is a composite image of the supernova. The yellow is all we see in visible light with the biggest telescopes in the world, and all the other colors include the X-rays and infrared as well that are part of that. And Cassiopeia A is also part of the Perseus spiral arm. So if you're searching for remnants of supernova, this is the 4 observable remnants that identify a supernova. And the 4 observable remnants that you can see is you'll see a nebula in an optical telescope that tends to expand over the decades and centuries. And also there'll be an extended X-ray source with it. The X-ray source originate when interstellar material is swept up and heated up by the blast wave that's going through it. We'll also see a radio pulsar. That's the neutron star that's moving very fast, gives off radio waves, and also a region of radio emission that's also expanding as well. And we'll see. That's what we're kind of looking at here. The first supernova remnant that was discovered by radio telescopes was the Crab Nebula, and it was observed by this sea interferometer here in the year 1948. And supernovae remnants emit radio emission throughout the radio spectrum. It's that as you go into longer wavelengths, or redder radio waves, if you want to think of it that way, that the supernova intensity increases as we go to longer frequencies. Longer wavelengths, shorter frequencies. So the Crab Nebula here emits a type of radio emission called non-thermal emission, and that non-thermal emission occurs when you have electrons going through a magnetic field. Those electrons, as they go through the magnetic field, give off this what we call synchrotron radiation, and we see this in not only just the Crab Nebula, but we see the Tycho supernova remnant, we see Cassiopeia, and Kepler supernova remnant. We also see it in supernova of 1181 as well. And this is, and when we're searching for them, these are the 4 criteria. So you've got X-rays, optical, radio, and there's the pulsar. So if you see all of those things, you know for sure that you've found the supernova remnant. This only occurs for a few supernovae, but more than 200 objects have been identified as being supernova remnants. And only the Crab Nebula, the Vela, and the supernova of 1181s are definitely known to have all 4 features that you see here. So there's different types of supernovae that can give off that give off different signatures that indicate what types they are, and knowing their types, we can also determine their luminosity and figure out their distances, which is actually important even for CHIME, because CHIME actually is studying the expansion rate of the universe, and we use some of these supernova types, like type 1a, to do that. So the type 2 supernova have hydrogen in their spectrum. The 1Bs and 1Cs will classify as a type 2 as well. And they're only found where new stars are formed, so generally in the galactic plane as well. Whereas type 1As can be seen in distant galaxies. So they're a little bit different. But what amazed me about when I was actually looking at this topic is that we actually can figure out which supernova types the ancients had seen and had reported. And to me, that was actually amazing. In type 2 supernovae, we know that there's hydrogen associated with the detonation of those stars. But when a type 2 supernova explodes, we actually see a star appearing, at least its core appears to be like an onion, and the supermassive blue star that was part of this core here might have looked like an onion layer of all these succeeding heavier elements in them. And so the lighter elements that would be fusing material would be higher up in the star's interior, whereas once it gets down to iron, the star's at its end throw, because the star cannot produce heavier elements past iron without losing energy and collapsing in on itself to form a supernova. A type 1 supernova is a 1A is a completely different type of supernova that involves a white dwarf that detonates and explodes. Once the white dwarf is fed with material coming maybe from another star or some matter that's out there in space, once it exceeds a certain limit, which is 1.4 solar masses, the star will explode and rip itself apart, and there won't be any hydrogen seen in its spectrum. And with the type 1A supernovae, they're a little bit better at being cosmic candlesticks, as I'm trying to figure out how far away they are, in that they have to be a certain luminosity before they detonate. And in recent years, they found that there's some of these type 1As that are actually a little bit more massive than 1.4 solar masses. But for our talk, we'll just keep it at that for now. I know there's some exceptions to that. Here's the light curves of different supernovae. Type 1As are about 5 times brighter than a type 2 supernova. Remember, the type 2 is the one where the star explodes because it's been fusing heavier and heavier and heavier elements. The type 1A is the white dwarf star that exceeds that certain mass. So the type 1s are far more luminous, and the way they can tell a type 1 from a type 2 is how dim the star actually dims down from its peak brightness. Type 1As have these more gentler curves here, whereas a type 2 has these dramatic drop-offs in their intensity. If you were to look at the output from a type 1A supernova compared to the energy output of the sun, it works out that these type 1 supernovas would expend about 100 million years worth of light that the sun produces all in a second. So they're incredibly luminous objects. And also, it was asked of me, why is it that, is it true that if a type 2 supernova, if the progenitor star was much bigger than, say, what you see here, is it possible for a type 2 to actually be brighter than a type 1A? And the answer is no, no matter how big the star gets, because the more massive a type 2 becomes, toward the end of its life, the more material is going to eject as a stellar wind. So a 50 mass type 2 supernova actually becomes like a 20 mass supernova by the time it's ready to explode. So a type 2 will never be as bright as a type 1. So this is one way that you can tell the different types. Determining the supernova types involve things like the examination of the supernova spectrum. Is it hydrogen? Is it not? How the light curve of a supernova changes over time. We saw here that there's the difference. You have one that has a much steeper drop off than the other. You also can determine the supernova's distance and luminosity from type 1As. Type 2s depend on the star's mass when it detonated. Also, how does the appearance look in X-rays or optical, infrared, or radio? You can compare whether or not that's a type 1 or a type 2 as well. And whether or not there's a degenerate star visible, the pulsar. If this pulsar is visible, you know it's not type 1A. And also the position in the galactic plane. So we saw all throughout most of those observations that we looked at that type 2s would definitely occur in the galactic plane, but you can also get the odd type 1 that's seen in the galactic plane too, so you got to be really careful. But you won't see type 2s higher above the galactic plane either. So that's some ways that you can actually use these factors to figure out the different types that you see. And this is the part here that actually really amazed me, and how they could figure out from just looking at a few observations from 2,000 years ago, or 1,000 years ago, what type they were. So here's the summary of all the supernovae that we're aware of that we can definitely determine that are supernovae. And I remember that I mentioned the cultures, I mentioned the Mexicans, the Australians, the ancient Americans, the Chinese, but I didn't mention the Romans, or I didn't mention the Greeks, or I didn't mention the Babylonians, who we do know looked up at the sky. It's just their records are very scant. If they didn't see a supernova, they didn't tell us the position of it, they didn't tell us how bright it got, we just might have recorded an event. And the supernova of 185 may have there might be two writings in Roman history that might have mentioned it. But again, the supernova event took place very, very far in the south. So it would have, their observers would have had to been way down there to see it. You can see also that in our history, some supernovae were very bright. This one here in Vela was about -10. But look how long ago it detonated, about 12,000 years ago. So if that was recorded, that would have been a big one. But in the last 1,000 years, these are the ones that we see here. I often get a question if there was a supernova that we know of that originated 2017 years ago. And so far we don't know of any that may have taken place. This is why there's a number of paleo and archaeoastronomers that are looking at conjunctions rather than supernova comets, rather than supernovae to maybe describe the event that was recorded in the Bible as well. I also listed the supernova 1987 here, but you can see its distance is 170,000 light years away, whereas most of the other supernovae are within the 2 or 3 spiral arms that we're in. That we're nearby to. And we can see that some of the supernovas that we've seen were type 1As, even though they occurred in the galactic plane. But all the ones that occurred as 2s are definitely in the galaxy's plane, as you can see here. And then here's our discoverers. I went back 2,000 years on this table here. We have the Chinese that looked at and recorded the supernovae 1,000 years prior to the last 1,000 years event. And you'll notice that between the year 400 and 1,000, there are no recordings of any supernovae. So there's a span there of about 600 years where we haven't seen any major supernovae appear in the sky. And yet, it's thought that in a spiral galaxy like the Milky Way, we should be seeing one every between 25 and 50 years. And we don't see it. And again, the culprit for that is all the dust that we see in our galaxy, in our galactic plane. I haven't put Canadians in here just because supernova 1987 was discovered by Canadians. And you can see there's been a number of observers all around the world that have seen the supernovae. And here's, if you were able to look down at the galaxy, I don't have a more modern map of the Milky Way. I know the Milky Way, we don't believe it looks like this anymore, but they put the positions of all the supernovae that we talked about in here. So I used that map for that reason, but I did this talk for the group in Kelowna, and they were really disappointed with this map of the Milky Way. So, but anyways, it still shows you that the sun is about 2/3 of the way from the center of our galaxy. And 3C58 is the supernova of 1151, Cassia 1680, Tycho is 1572, Crab is 1054, and Kepler here is the 1006. The 1604 supernova. So all the other ones happened prior to all of that time. So there's speculation by various cultures. I'm just going to go back up to this one here. There's speculations that various cultures may have seen very ancient supernova events like the Vela supernova here. And what I wanted to mention is that the Bolivian indigenous people have a petroglyph that appear to show a supernova that may have been in the order of 7,000 or 8,000 years old, according to the archaeology that was discovered on rock art. But today, with modern readings, it appears that the supernova event might have been triggered about 12,000 years ago. So there's a little bit of a dichotomy between the times. Also, the Veil supernova and Mesopotamian artifacts on clay tablets, they sing this giant storm Vela. However, that date for that clay tablet is only about 6,000 years ago. So again, we have two cultures that are kind of recording things about 10 or 1,500 years apart, but they're still way off from what we determine the age to be. So it's not known for sure if anybody saw the Vela supernova or not. Also, HB9 here in Auriga, it has been thought to have been seen in Indian, as in East Indian, Neolithic art, and motifs show a full moon and a supernova near the ecliptic. And the supernova is based on some very loose assumptions, however. So it's thought the dating is right for their work, but again, the interpretation is not clear whether or not anybody saw that. So that's why I didn't really mention that too much in the talk. And so basically, I just wanted to show you where we are, and we're about 27,400 light years away. Most of the supernova that we have seen are within these three spiral arms here, and that's pretty much as far out as we can see. And using optical astronomy, radio helps us figure out, where objects are much further than that. So, anyways, that wraps up my talk on historical supernova. Does anybody have any questions about anything that we've seen here so far?
Well, before we do that, thank you so much for what I consider an amazing talk. And we were very fortunate in March at our Astro Cafe to have Ian Shelton give us a talk on his supernova, and he was full of enthusiasm. I think the topic of supernova makes people enthusiastic. Do you not think this man is enthusiastic? So, does anyone have any questions for Wendell?
So you guys all know everything about historical supernova now? Yeah. Yes. The red one here. This here's Cassiopeia A.
Okay.
So this is the brightest radio source. Okay, I'm glad you brought that up. This here's called Cassiopeia A, and it's the brightest radio source in the sky. It's about 4,000 Jansky units. I even wrote it down. I'm sorry, 3,390 Jansky units. Compared to the other radio emission that we see out there, this is by far the brightest object that's out there. So when the Dreo astronomers had stitched the picture together, because each image that you see here is about 2 weeks worth of observations made by the synthesis telescope, the Seven Dwarfs. And so if this is 2 weeks worth of observations, and that's 2 weeks, and that's 2 weeks, and that's 2 weeks. So you can see this here took over a month to image this. But because how they image everything together, they have to move the antennas on the tracks and actually put everything together. But then after they do that, then they stitch this information to the information that they have here and the information that they have here. And because this is so bright and the telescope has low dynamic range, we get a lot of interference patterns going into the other observations around it. So this is just a really, really bright object. If this is all one color, it would look. This here is Tycho's supernova remnant from 1572, and this is the supernova remnant from the year 1181. And so this here is what I call the 1680 supernova. Whether or not it is, I don't know. But I like to think that Flamsteed discovered something, right? Because there's so many things and so many examples in astronomy that I can show you where people have made observations of the sky not ever realizing in their lifetime that they made an important discovery. Jansky was another one that made this observation galactic emission coming from the center of the galaxy. And my encouragement to all of you is to make observations of whatever you're looking at. Whether when I'm at the observatory now, I make observations of the sun. I get a roll of Scotch tape and I draw a red circle around it. And every time I look at it, I make most of the prominences now. I might not never see anything, but maybe 300 years from now, I might accidentally discover something I didn't know what it was. So I would encourage everybody to do that. And you might see things out there that nobody else has ever seen, and then you might look through your observations one day. It might be very important. So very important to do that. And the furthest object I've ever looked at in a telescope is a double quasar that's 8 billion light years away. And that can be seen in a 12.5 inch telescope. So I would encourage everybody to, no matter what you're looking at, to observe it. Not only does it, you'll remember what you see, but also the next time you see it, I guarantee you that you're going to find more to that object that you documented the first time. So it really helps your observing skills as well.
Okay. Well, one neat thing, when I saw these slides initially, I was really taken away by integrating all of the different wavelength bands together. So much more complete picture. It just shows you the value that optical astronomers need to talk to radio astronomers and vice versa. So thank you very much. Any other questions?
I was going to say something because you're so interested about astronomy itself. You were mentioning it takes a possibility that it will be between 25 to 50 years to see a supernova. So you are one of the persons that I know that observes the sky pretty quite often. Do you think in your lifetime you will be able to see something as big as a supernova?
I think we're ready for a supernova. What has happened is that for Milky Way standards, we should see a supernova even in our position of our galaxy once every 200 years. And the last significant one that we saw in Milky Way was in 1604. So we're 200 years overdue for one. So I think it's a very good chance that if any one of you can be looking at the night, you're going to see it first if you're looking up. So that's another thing I wanted to encourage everybody to do as well. Also, if you found that I went through the presentation too quickly, and you want to get some more notes, like the stuff that's on here, but you didn't have time to write it down or whatever, just give Reg just contact him. He's got my email, and I'll send you this information if you want as well. Because I know there's a lot of stuff on here.
Well, you did a very good job of keeping your talk to the short time. I more or less hinted that we don't usually run to 10 o'clock, but it's obvious that there's a lot more information in there than we heard tonight. You can talk for days on this, I'm sure. And thank you so much for coming down, Wendell, from Penticton, taking the time to come here. Some of the expenses for this are covered by the RASC public speaker program, and we're grateful for that. But it took time for Wendell to come down here, but can you imagine the amount of time it took for him to assemble all this information, put it together in such a beautiful way? Just blows my mind. So thanks so much again for coming. And as token for appreciation, we have this coveted Victoria RASC coffee mug.
And Victoria's a very beautiful city. I'm really glad that you guys invited us to come down to see your city. I haven't been here for like over a decade. And so I'm really happy that we had the opportunity to come down and see everything on the sites down here too.
Now we have, we normally go up to the astronomy lounge for coffee and cookies. So if you can make it up there, we'd be happy. If anybody else has more questions, we can ask Wendell up there. Thank you very much.